In this video, we're going to go over another stress transformation problem. This time, we are given a signpost and asked to find the rotated stress states for the principal normal stresses, the maximum shear stresses, and a rotated stress state at 30 degrees counterclockwise at point A. We are given the stress state at point A, so from that we can also figure out what the weight of the sign is going to be equal to and the magnitude of the uniform pressure that is applied to the sign, kind of like a wind load almost. So let's get started. So from the stress state that's given at point A, we can go ahead and draw our stress block for this problem. Here's our stress block for this problem. You can see that we have a positive 3.381 KSI on the positive X face, causing tension. And then around the outsides, our shear stress is 5.942 KSI. And then you can figure out the direction by if you look at the positive X face, the arrow is going in the negative Y direction, so that means we're going to get a negative overall, and that'll help us determine what the stress arrows look around the whole stress block. So now using this, we just can create our coordinate points that we're going to need to plot on our Mohr's circle. So if we look at our X coordinate first, the first coordinate is going to be our normal stress, so that's a positive 3.381 KSI. And then our second point is the shear stress along that same face. And instead of denoting a negative shear stress based off of the axes, we're going to say a positive stress is one that causes a clockwise rotation. That's how we do the Mohr's circle. So that means in this case we have a positive 5.942 KSI. So now we go on to our Y coordinate. So there is no normal stress acting on the Y face, so that's just going to give us 0. And then our second term on the positive Y face, it's causing a rotation that's counterclockwise, so that's going to be a negative 5.942 KSI. So now we have our coordinate points. We can go ahead and plot what our Mohr's circle is going to be. So you can see below here is those 2 points plotted on the Mohr's circle. And we've created the circle based off of those 2 points. I've also I went ahead and plotted where tau max is and where our 2 principal stresses is, sigma min and sigma max. So before going on to solve for what those values are, we need to define the circle a little bit more. So we need to find where the center of this circle is at, and we need to find the radius of the circle. So the center of the circle is just the average of the normal stresses of our 2 points. So that's going to be, center is just going to be equal to 0, for that's our normal stress of our Y point, plus 3.381, all of that divided by 2. So that's going to get us a center that's at 1.691 KSI. And then to do the radius, we just need to go ahead and solve this particular triangle right here and solve for that radius. And since we know the 2 legs of the triangle, we can go ahead and use Pythagorean's theorem to solve the radius. So that radius squared is just going to be equal to the height of our X point, which we know to be 5.942 squared, plus the bottom leg of our triangle, which happens to just be the center, so that's 1.691 squared. So that gives us an R value of 6.178 KSI. So now that we have those 2 points, we can go ahead and solve for what our principal stress is and what our max shear stress is. What are those values? So our max shear stress, tau max, that's just going to be equal to the radius. As you can see, that height is just equal to what the radius of the circle is. So that's just going to give us a 6.178 KSI. Our sigma max is going to be equal to our center plus the radius. That's going to be 1.691 plus 6.178. So that is a value of 7.869. And then similarly with our sigma min, we do the same thing, but instead we subtract the radius from the center. So it's 1.691 minus 6.178. So that gets us a value of negative 4.487, and these are both in KSI. So now that we have those points, the only thing left to find is going to be the angle needed to achieve those principal stresses and max shear stress. So we'll go ahead and start off by finding what this angle is, this angle theta. We're going to need that in order to solve for what the angle that those two stresses need to be achieved. So that theta, if you take the tangent of theta, we know the two legs of our triangle, so we can just say that that is equal to 5.942 over 3.381. Oh, excuse me, not 3.381. Meant the radius, or sorry, not the radius, the center, so 1.691. Doing that should get you an angle that's equal to 74.1 degrees. So now let's look at what angles we need to find. So we need to find our red line if it was rotated all the way to our shear stress over here. So we'll call that 2 theta s. And the reason it's 2 theta s is because in real life, the amount the stress block rotates, it's going to rotate twice as much on the Mohr circle. So that's why we call it 2 theta s. And then the other angle we need to find is if that same line was rotated, but instead rotated down all the way to be completely horizontal. So we'll call that 2 theta p. So we'll start off with the easy one. We can obviously see that 2 theta p is just going to be identically equal to what theta is. So this is going to get us a theta p value that is equal to 37.1 degrees going in the clockwise direction. Similarly, we can do the same thing with our theta. So we can say, okay, theta, or excuse me, 90 minus theta should get us a value of 2 theta s. So doing that math, you can get that theta s is going to be equal to 7.9 degrees counterclockwise. So now that we have those two angles, you can just go ahead and draw what our stress blocks are going to be, since we know the values and we know the angle. So I'll just go ahead and draw those real quick. So here are those two stress blocks drawn. You can see on the left one, that's our principal stress state. We've rotated it clockwise 37.1 degrees, and so we only have normal stresses acting on our stress block at that point, which are our max and our min stresses. And you know what face they're on based on the faces of the axis that we have rotated. So you still know where the y and the x-axis are located, and that corresponds to where you rotated your x and y points. So, and then the same thing for our max shear stress. We have the max shear based on a counterclockwise rotation of 7.9 degrees. And then even though we have max shear stress, we also still have a normal stress on each face, which is going to be our center location, which is 1.691 KSI. So now that we have those two, we can move on to part 3 of our problem. If you remember up here, part 3 says that draw the rotated stress state at 30 degrees counterclockwise rotation, labeling all angles and stresses. So if we look at our Mohr circle, so we want to rotate kind of our line 30 degrees counterclockwise, and so that means on our Mohr circle, we're going to be rotating it 60 degrees counterclockwise. So that'll put us about here. It doesn't have to be exact, so I'm going to just draw this. So this is going to be our x prime point, and this is our y prime point. And so we have rotated right here about 60 degrees. So we're interested in figuring out what our coordinate points for our x prime and our y prime point are. And so we're going to be looking at this triangle right here. So we know the r value. We can figure out what the theta is. We'll call this theta 1. We can try to figure out what the theta 1 value is in order to figure out what of our two leg values are. So we'll go ahead and redraw that exact same triangle lower down. So we're trying to find rotating 30 degrees counterclockwise. So that leaves us with a triangle that looks a little bit like this. So we have, this is our radius, this is going to be our theta 1, we'll call this value L1 and this value L2. So first things first is we need to figure out what theta 1 is. So if we look at theta 1 back on our Moore's circle, you can see we know that 180 degrees passes between theta and theta 1. And so we can say that 180 degrees minus the pink theta minus 60 degrees should get us what our theta 1 value is. So we can say that theta 1 is going to be equal to 180 degrees minus 60 degrees minus our theta value. So that gives us a value of 45.9 degrees. So now that we have that and we know what the radius of our circle is, and so we know the hypotenuse of our triangle, we can just use trigonometry to figure out what L1 and L2 are. So L1 should be equal to R times the cosine of our theta 1. So that gives us an L1 that is equal to 4.3. And L2 should be R times the sine of theta 1. So that gives us an L2 that is equal to 4.437. So now that we know those those lengths, we can figure out what the coordinates for our x prime and our y prime are. So for our x prime coordinate, that is just going to be equal to our center point minus L1 in this case, since this is going to be our center. So we're subtracting L1 from it. And then our second point, which is our y-axis that is our shear stress in this case, that is just going to be the length of L2, that height. So doing that, you should get a value of negative 2.609 and 4.437. That's positive. And then do the exact same thing with our y prime coordinate. Only in this case, it's going to be the center plus L1, and then our second point is going to be a negative L2. So if we do that, you should get a value of 5.991, and then a second point of negative 4.437. So now that we have those two coordinates, we can go ahead and plot our stress block with those forces and stresses on them. So to the right, you can see this is what our stress block looks like with those stresses applied. We've rotated it, we've shown that it's rotated 30 degrees counterclockwise, and we've placed all of the normal and shear stresses on it. So that completes our first three parts of this problem, and then I'm going to continue doing the final part in a separate video.